than anything else. I think that would probably be good. Okay. You guys are on the clock.
All right, I'm Ryan Nielsen, a junior in packaging science.
I'm Mason McLeod. I'm also a junior in packaging science.
I'm Desi Ferreira, a senior in mechanical engineering.
And this is our dynamic vehicle dynamic characterization creative inquiry. So has anybody ever gotten a package in the mail that is messed up or banged up, and then you open it up and whatever you have inside is destroyed? Well, yes, sir, I feel your pain. That could be due to the package handler, or that could be due to the way the vehicle and the package interact with each other. So if you have the FedEx truck going down the road at 40 miles an hour and hitting a pothole, we have this huge impulse, and your package is flying off the shelf, lands on the floor of the truck, and they have a huge dent in it now. So that's kind of the focus of our presentation, is understanding the relationship and how those two things interact. So first, our problem statement is to measure and predict responsive package on a trailer for varying conditions. So that's kind of the focus, is we have a trailer, we have a package, and we're trying to understand the relationship between those two things. First, we're going to talk about our literature review. So we're not experts in this field. So what we did is we went out and we looked at research people have done in the past to try to gain a better understanding of what's happening here, of what we're studying, just try to enhance our knowledge so that when we do things, we can understand what's really happening. Next, we're going to talk about the testing. So we're running a lot of tests that we found. As far as the literature review goes, we can run all the tests that people have done and use that as a baseline for analysis. And then data analysis, we're going to take the data that we get from that and analyze that and see what we can understand from it. What kind of relationships can we derive from that data? And finally, in conclusion, we're going to talk about what we learned, what we got out of it, what kind of value we took away from this. Our goals we kind of split up in two parts. The first, as you can see, is characterize the trailer, and secondly is measure responsive package. So we're going to model a trailer in a virtual space using MATLAB, and then we also have our physical trailer. And our goal is to have a virtual model, give it an input, and then receive an output, and see if that matches what's going on in real life. And likewise, with the responsive package, we're going to characterize the package and give it inputs, outputs, and of course the whole entire system together, and see how those things interact with each other. All right, so part of this review is understanding what is the industry today. So there are two types of suspensions used in industry. One is leaf spring, the other is the air ride suspension. Leaf spring is essentially a stack of metal plates, and those are attached to the tire. And what happens is when the tire hits a bump or something of that nature, the metal plates are spring tempered, so they resist that motion. That creates a dampening effect. And the air ride system is little more than a bunch of inflating or deflating bags, kind of like in a strut. And what that does is that creates a dampening effect. Now, it's interesting to note that the air ride versus leaf spring, as you can see here in the graph on the left, the G's experienced by a leaf spring system are approaching 1.5 G, whereas the air ride is almost 50% less. So you can see that on the graph to the right, the average RMS value, RMS is really a measure of intensity of vibrations. You can see leaf spring is again outperformed by the air ride system. If you look at the differentiation between the loaded and unloaded parts right here, you can see again the air ride has very little variance in between those two loaded and unloaded systems. Now, reliability. So the leaf spring is basically a non-serviceable system. If it breaks, you just replace it. Whereas the air ride system, you have to do constant maintenance to keep it going. Now, if the air ride system fails, you will see higher average RMS values than the leaf spring system in the unloaded fashion. So over 100% increase in RMS values if your air ride system fails. And of course, the cost, the air ride system, while it is better in conceivably every way except for maintenance, the maintenance cost is 30 cents per mile. So that is something you want to consider if you are in the industry. If you have something very sensitive to shock and vibration, you probably want to use the air ride system, but you also want to make sure you maintain that system. Otherwise, you could see RMS values that are off the charts. So, Okay, so we don't have a leaf spring system or an air ride system. We have a torsional axle trailer. So what that is you see it's a piece of square stock, and then you have a piece of square stock on the inside. Then you have 4 rubber rods that run down the length of the axle. And what happens, you can see in the second picture here, is whenever it experiences a shock, the interior piece of stock rotates, and it hits these rubber rods. And that creates a dampening effect. And the bottom right here is kind of a heavy shock load. As you can see, the rods are almost completely compressed. Now, you may ask, why do we have this? Well, why does industry not use this? Mainly it's because if you look at our finite element analysis, you can see that instead of distributing the stress among the frame like the leaf spring or the air ride system, you can see that it concentrates the stress right there. So that's important for industry because if you have a tractor trailer loaded with 40,000 pounds of material and you develop a stress crack right here from constant shock hitting that point, you could cause a loss of your product, you could cause an accident, you could cause some sort of other cataclysmic event, which would be bad for everyone. So, there you go. All right, so we talked about the suspension. We're going to talk a little bit about the vehicle frequency analysis. So we did some background research on how do vehicles respond, what kind of frequencies we're going to see on the typical vehicle. We found that we have large resonance frequencies. So resonance is just the amount of amplitude you're going to see in your response at 3 to 5 hertz and from 10 to 15 hertz. So at those you're going to see lots and lots of upward motion. Also, likewise with that, our high frequency analysis, we found that we could see some resonance nodes due to wheel invariance. So if you have misaligned tires, you can start to see some more of the higher frequency resonance on that. Also to note is that the negative effects on frequency due to speed. That is because you're going to go through here and let's see. Oh yes, road roughness. Okay, so you're not going to see an increase in the frequency, but you're going to see a marked shift in the amplitude of those waves. So make sure you keep that in mind for the future. All right, so we talked about the vehicle, we talked about suspension. Now we're going to talk about the tires. Everybody's car has tires, right? We can't leave that out of the equation. So you can see we're talking about load, forcing frequency, speed, and tire pressure. The graphs here on the right show that the stiffness increases as load increases, and then it kind of starts to taper off. And then the stiffness kind of straight here, and then it goes up as speed increases. And then the damping coefficient decreases as speed increases. And over here you can see your damping coefficient decreases as the forcing frequency increases. And then our stiffness and damping coefficient both increase as tire pressure increases. So those are important to understand because this is kind of like a baseline for behavior. So we want to compare this to our data to see what we get to make sure that that data is reasonable. We can't just run off and have unreasonable values. We have to have some sort of baseline understanding to really take something away from this. All right, so to prepare for our testing, we went to the Clemson University International Center for Automotive Research. And we did that to find a subject matter expert who has done this for years to help guide us and mentor us and give us a direction for our research. We found him, and one of the things he talked to us about was the first thing you got to do is determine the center of gravity for the vehicle. And that kind of is a springboard for other experiments. One thing we found with that trailer, whenever we were taking it over to CUI car, is that whenever we hit any minor bump, the trailer would basically jump into the air. So we needed to stop that from happening because if your trailer leaves the ground, it gives you bad data. So you need it on the ground so you get the frequency, impulse, and response and dampening. And to do that, we created this thing called the load-bearing attachment, which is a little more than 2 threaded rods on 2 plates. And we loaded 200 pounds on those load-bearing attachments, primarily to stop the bouncing of the vehicle. So we talked about the tires, suspension, and the vehicle itself. Now to better understand what's underneath the hood of our experiment, I'm going to turn it over to Desi, and he's going to take it away.
Thank you, Ryan. So we know we haven't shown you our actual trailer yet. However, the picture to the left is a 2D representation of what's going on with our trailer. You can see the main bodies being, or the main masses being the the actual body itself, which is on top, the Clemson paw, the suspension, the wheels, and some ground, which could be a pothole or it could be a table giving the given inputs. And the way that these four bodies interact is that we're mainly interested in the body of the system, because that's where going to be your packages on. That's what you want to find the amplitude of vibrations. And so the body is controlled, or the motion of the body is controlled by the stiffness and damping of both the suspension and the wheels. As Ryan said earlier, the suspension itself has a certain stiffness to it, and it dampens the energy of the vibrations that it's receiving due to the rubber slabs. And so this equation of motion is shown up on the top left. The actual equations don't matter too much, you don't need to worry about them. However, what is important is that to determine the motion of the top body, the package, we need to know these four parameters, being the stiffness and damping coefficients of both the tire and the suspension. And so here we'll go into give a little insight as to how we're going to find those stiffness and damping coefficients. To determine the coefficients of the suspension system, we're going to use a logarithmic decrement method. And this method is basically just measuring the rate at which energy is dissipated from the system. This is shown in a plot to our right. This is a sneak peek of one of our results later. We'll get more into it when the time comes. But for now, just notice that the line that I've shown, the black line, that is an exponential curve fit that we were expecting to see. And as you can see, the lower peaks are corresponding to that line. So in this case, this response of the trailer to without the wheels is showing an exponential decay. And we can do this response because it's a 1 degree of freedom system. We just showed that the actual model of the body is a 2 degree of freedom system. You need to determine both the motion of the body and the suspension to determine the actual motion of the body. And so we're simplifying this or the way we obtain these coefficients is by simplifying it and taking it one at a time, determining the coefficients of the suspension and then coefficients of the tires. The suspension, you just give an impulse response. That's just a burst of energy in which you determine the energy rate of dissipation, as we said earlier. However, the tires get a little more iffy, as you can't really give an impulse response to a tire. It's just going to bounce up and down. So the way we went about this, and we'll get more into this later, is we did a similar response of this 1 degree of freedom system, except we assumed that the entire trailer, suspension, tires, and all, is a 1 degree of freedom system, which means that we're assuming that the mass of the suspension is equal to 0. Basically, we're just trying to get an approximation for the damping of the tires using this method as well. And finally, the stiffness of the tires, one thing we've yet to discuss, is going to be a simple compression test. We'll get more into later. However, it's just going to be determined using Hooke's law, showing that force and deflection is a linear function with the stiffness as the slope. And now into the test is Mason and Plan.
Appreciate it, Desi. Okay, so one of the first tests we did was the impulse test. Here we kind of wanted to isolate the body of the trailer and just test the suspension. To do that, we took the tires off. We took the torsion bar and placed it on these jacks that Ryan actually welded up for us in the lab, and bolted these down to the compression table. Here we ran a square impulse, and what that means is you're hitting it with a distinct and brief shock. Think about driving your car over a curb or off a concrete ledge, something like that. No real problems with this test. One issue we did face was, when you come down, you got to come back up that same displacement. So the trailer kind of wants to keep going when you're going up. So to kind of keep it grounded to the jacks, we had to put some zip ties on it. Those kind of started to break away, so we had to upgrade to something a little bit more heavy duty. Threw some steel wire on there and secured it so there wasn't any kind of excess vibration that would throw off any of our models. Also, we did the same test but with the complete system. So we put the tires back on, and then through that we were able to kind of approximate this dampening, the dampening of the tire through compared to the other model. Moving on, we did the compression test, which is the stiffness of just the tire. To do this, we took this rig that Ryan also made from some scrap metal laying around and placed it in the compression table and programmed it to do a certain vertical displacement. Now, instead of just taking the tire and placing it in the compression table and having it just come straight down while it's sitting on the ground, This would have caused displacement for both ends of the tire, which would have thrown off this measurement. So we kind of had to come up with something like this to make sure it's only displacing one end of that tire. Test went very well, rig worked perfectly. Kind of taking those 4 components to form this virtual model. Using those parameters, we kind of moved forward and started working with the science suite. Now this, we put everything back together, tires on the trailer, chalked up the tires to make sure there wasn't any kind of rolling going on, and then hit it with this 300 to 300 hertz frequency range. So, you run through this whole range and you're looking for this resonance frequency. Where are we getting this maximum output at a given input? For us, it was kind of toward the lower end of the range. We'll get into that a little bit later. Issue we did have here was a little bit of movement from the trailer. So when you're hitting it with this resonance frequency, you're getting the maximum output, so you're going to get a lot of vibration. This kind of caused a little bit of left and right movement for us. To fix this, we kind of put a little bit of mass on the tongue, which you can kind of see sticking out over there. Put a little bit of mass on that, made sure it wasn't moving left and right on the table, keep it on there. Next, we did the exact same test, but on the package itself. This also allows us to get a resonance frequency of the product inside. On top of that, it allows us to get a baseline response to see, how is the product responding to this wave of frequencies in comparison. What is it going to do on the trailer? So getting this baseline idea of, how is our product behaving. On top of that, we had to make sure the package was secured, so we didn't get any kind of excess vertical or horizontal motion that would have thrown off some of our measurements. So to do that, we took 2 iron bars and then nothing on top. Excuse me. And made sure there wasn't any kind of movement with the package that could throw off the product's movement. Okay, so here we kind of took it all and put it together. And not picture, we took some bungee cords, strapped down the package to make sure we also didn't have any of that vertical displacement. We compared this to the reaction the package had by itself on the table and got to see how are these dampening coefficients and stiffness coefficients affecting the response that the product is having. On top of this, we got to get the resonance of the whole system, which everything involves, and we use that kind of moving forward into the next test. So here, the sine wave, we take the same exact setup as before, except this time we hit it with 2 distinct frequencies. So these are those resonance frequencies we talked about before, where we're seeing this maximum output. And taking these frequencies and being able to input them not only in the physical test, but also into our virtual model we talked about earlier, and being able to predict, what kind of output should we be seeing versus what are we getting. And using this to test the accuracy of our model and, see what we really have as far as us being able to predict outcomes of our trailer. And Dad's going to talk a little bit more about the details of the results.
So we'll get into the results here. The first test that we did was the impulse response of the trailer without the tires. We gave a sneak peek of this earlier, now we'll get into it. As we said earlier, we did see an exponential decay rate of the response after giving it an impulse. So we deem this an accurate method to determine the parameters, being the damping and spring coefficients of the suspension system itself. We'll plug that into our model. The next test was the equivalent system, being the whole system on the impulse test with the tires included. And here, as opposed to seeing a perfect fit, you can see that this is a slightly off for the exponential decay rate. It's not a huge amount off, it just shows that this is not truly a 1 degree of freedom system that we can model as such. And so there will be some discrepancies. However, as the purpose of this was to determine the damping, or approximate the damping coefficient of the tire, we've deemed it reasonable enough to get us in the correct ballpark. And so we were able to get our damping coefficients of the tires with this test. Finally, the spring constant of the tire itself, we used using the compression test, as Mason said. Here's our graph. It's pretty linear, some slight nonlinearities, but for our purposes, it's a well enough approximation to get the spring coefficient of the tire. And so finally, we have all of our tires. We can get into the, sine sweep results. Now here you can see we've plotted both the results of the trailer and the package for the sine sweep from 0, and I've only included the low frequency domain as we didn't really see any resonance, any high amplitudes in the high frequency domain. And so obviously you can see our largest peak is right around 4 hertz, subsequently 8, 10, and around 18 hertz. This is for both the trailer and the package on top of the trailer. And so you can see that the frequencies aren't changed. The red is the package, blue is the trailer. The package is just right on top of the trailer in most cases. This is accurate with what we did with the package by itself, as we didn't see any resonance frequencies of the package itself on the trailer. We just saw a flat line, or not a flat line, but an even distribution at all frequencies. This could be because we weren't actuating enough and we need a higher amplitude of acceleration on the vibration table. However, at least for the given results, we can see that the package and the trailer have synonymous frequencies that they respond at. The package just has slightly more amplitude due to a small amount of resonance along the frequency domain. And so we took that frequency of 8.5 hertz as the highest frequency of 4 hertz gave us, jumping off of the table. So to get accurate measurements to predict to determine the accuracy of our model, we ran a sine wave constant 8.5 hertz for a given time. And on the left is what we've measured. That's what the accelerometer on the trailer itself at 8.5 hertz. And on the right is what our model predicted. And you can see both of the frequencies are at 8.5 hertz, which is the same as the forcing frequency. So our model accurately predicted that. However, the amplitude of the vibrations were slightly off. The amplitude of the measured response was just under 5 meters per second squared, whereas the amplitude of the predicted response was just under 4. So we're about a meter per second square off. We have to determine if that is a reasonable approximation. Again, we made some assumptions going into this, so we don't determine, or we're not expecting to be exactly accurate. And there's some uncertainties with the measuring equipment as well. But this is a pretty good model, at least in our opinion. We will run more tests at more frequencies to determine if this holds true or if we can get closer to the actual response for all frequencies. However, for our purposes and going forward, we'll take this as being an accurate representation of what's actually happening.
All right, so to kind of wrap it up here, highlighted in green are things we pretty much accomplished this semester. This more or less builds a base moving forward in the next semester and allows us to kind of have a nice frame going in. As you can see, modeling the trailer with the conditions we kind of step forward. Taking this impulse test and the compression test and taking these and forming this model to be able to predict our physical response. The virtual model was a huge goal for us coming into the semester, and being able to have that done and test that was pretty big. On top of that, we kind of got into a little bit of package stuff. We were able to run that sine wave or sine sweep on the package, and that's the first step in that. We're going to throw that into changing the varying conditions of the trailer and seeing how the package responds to that as well. Also, we started with the third bullet point down on the characterized trailer. We were able to run that sine wave on the trailer itself. Here we need to do the random input still, which is going to be a road test of sorts. We'll get into that a little bit later. And for the varying conditions, we'll also talk about it a little bit more later, just changing things about the trailer to see what kind of response we're getting. As far as the variance goes, the big four, as you see listed here, alignment was a big one for us. We didn't find too much in the research going into this about the response. So changing the tire alignment, seeing how that has an effect on the response of the trailer, and more importantly, the product, is a big emphasis for us. The speed, that kind of goes back to this road test, taking it out on 76 versus driving around campus over speed bumps. How is that going to affect the trailer? How is that going to affect the product? The load, so not only adding more weight to the trailer, but also moving it around. So putting 2 more of those load distributors on the back and putting all the weight in the back. How is that going to affect any of our vibration? And then finally, the tire pressure. And this is just, adding or taking away pressure to the tire. This will affect the stiffening and dampness, obviously, and how will that have an effect on our vibration? Kind of a little more of a wrap up on things more applicable to things outside of the CI, things we've learned along the way. Number one, always have a plan B. Nothing's ever going to go according to plan, we found out. You come into the lab and you might have a test you're going to run and the machine's broken or somebody's on the vibration table. Working with that and kind of rolling with the punches is a big lesson for us. Secondly, using the individual strengths of your teammates. I was fortunate to have 2 great guys in CI with me. Ryan, not only a great packaging student, master welder turns out, he and him throughout the CI. Desi, the genius engineer, had to have him, running this model and leveraging these strengths and being able to, everybody bring something to the table and working together to accomplish a goal. Third, making these bite-sized goals. So that's kind of breaking down this vehicle dynamic, breaking that down into smaller, more achievable goals. So we need to do our research, then we need to start running impulse tests and so on and so forth until you build your way up into making that model and testing it. And lastly, we learned a ton about presenting. As you may not know, Dr. Brad, big presenting guy, learned a lot about what makes a good presenter, how to improve. Like you said earlier, you can always become a better presenter. There's always something to learn. It's a huge skill no matter what field you go into, whether it be engineering or packaging. You're going to have to be able to communicate with people about what you're doing and your ideas. And with that, that's the end of the presentation. Thank y'all very much.
Good job, guys.
Any questions?
What do you use as your product?
So we used a printer actually from the I think it's 440 lab, and then we had to actually print out a new box because somebody threw it away or something. So we remeasured it and used some polystyrene inserts in there, and yeah, that was it.
And there's a spot on the printer for the accelerometer to go.
It's like a sublocation. So we used it before. So. Anyone else? Any other questions?
What computer program did you use to model the actual
Simulink.
simulating? Okay. Is that did you use SolidWorks at all to build it, or?
No SolidWorks.
Okay.
We just took those equations in motion, made the block diagram.
Oh, okay.
Yeah, and then those plots were the plots of the acceleration, and then we're comparing that with the accelerometer.
All right.
Acceleration of the body, that is.
When you talked about the forcing frequency of 8.5 hertz, you mentioned that amplitude was off, and that there might be some uncertainty with the equipment. What uncertainties would there be?
I've not calculated any uncertainties yet. It would just be standard uncertainties of converting analog to digital measurements, and some resolution. So it's probably not that large of a response, but just something to keep in mind.
When you guys, kind of changed some of your boundary conditions on what you were doing with like you added the steel wire and the zip ties, and you also added weight on the tongue, I think you had said, Mason. Do you think that would have affected the results that you would have gotten? Did it inaccurately simulate, or do you think that was necessary to get results, or do you think it wouldn't have had an impact at all?
I reckon it would have a slight impact. However, we'll take each example on their own. The weight on the tongue, we figured having the weight on the tongue, which is very long, it's 5-6 feet at least. No, it's like 10 feet at least. And so we figured holding it down at a constant rate, the vibrations happening on the center of gravity is so far away, we figured it wouldn't have too great of a response. The wires on the torsional axle, I do not think those had much of an effect at all, as those were just keeping the axle stationary to the ground relative to the table itself. And so we were just preventing it from jumping up and down. We were more worried about the frequencies of the actual body vibrating.
That's good.
I mean, to be fair, the trailer would be connected to a truck or some type of vehicle to pull it.
That's true.
It would be locked down.
Yeah.
It's not going to be free roaming out there by itself, so that does make sense.
I had a question for you all the way back to the beginning. You showed a couple bar graphs showing the I guess this was tire or suspension type. There was a bar for load. That's it. One for loaded and one for unloaded, and which is great. I hadn't seen information like that kind of illustrated this way before. Air ride and leaf spring comparison, but interestingly, loaded comes out equal to or less than, particularly in the leaf spring. Why do you think loaded comes out less than unloaded for intensities?
I think it's because the leaf spring, whenever it's not loaded, it has a tendency to deflect more. Whereas if it's under a lot of load, it would move less. Whereas if you have like a spring between your hands and you have weight on here, you had it restricted, you put like a vibration on it. As long as under some sort of load, it shouldn't move that much. Whatever it has no load on it, and the tires can just bounce freely, like if you have a pothole, for example. I kind of think of it like a seesaw, where you have like the fulcrum where the event impact is, and you kind of see like a magnified response the further away you get from the axle, from where the suspension is located. So that's kind of my basic understanding. I'm not by no means an expert.
Sure, I was just curious what you thought. Does anyone else want to chime in on that? Why there'd be a difference between those two?
You talking about which one here?
For the leaf spring, between the loaded and the unloaded, between the yellow and the gray.
When I think about it,
Trying to.
Yeah,
So-
probably similar to what Ryan said, just being, under that load kind of suppresses that a little bit. I'm not really sure.
Okay. How about you, Devin?
We'll be able to find out next semester as we vary the mass of our,
I love it.
mass of our
I
trailer.
love it. Okay, very good. Good. Okay.
Sir, do you know what?
So this is saying that your packaged product's better off if you put it in a vehicle that has mass in it, right?
Yes, for the springs, yes.
And if you think about what lowers the amplitude of motion is maybe not so much stiffness, but damping is removing energy from the system. And we remove damping when we undergo displacement. So more displacement, you get more opportunity to remove energy from a vibrating system, right? And so if you're heavily loaded in the back, these suspension systems are designed for these heavy loads, and so so when it's unloaded and you're bouncing down the road, you get very little deflection taking place, and so there's very little opportunity to remove energy from that system. If you load it up, now you go over railroad tracks or a pothole, and you get a lot of displacement in the back of the vehicle, and that's all opportunity to remove energy from the system. And so which is why when we were driving to Greenville, we looked in the back and that thing's bouncing around behind us because there was no give in that suspension. It was so lightly loaded that it was really stiff, and it's really stiff when it's lightly loaded. You're just bouncing down the road. You're not allowing that deflection to take place. So that's what I would think. I like what Des has said too. We'll see next semester. So very good.
Anything else?
What are your hypotheses for next semester based off of those four things, the alignment, tire